Faster, smoother LLM replies in Python. By the end, you will stream a long message into small client updates, measure perceived latency and total completion time, and choose chunk and batch settings that reduce UI work while keeping responsiveness. You will also see a simple first paint trick that makes the interface feel instant. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Streaming reduces perceived latency in real apps by improving time to first byte, which measures how long until the first partial content reaches the client. It also reduces wasted render work, so you do fewer DOM writes or terminal refreshes. The main trade-off is total completion time and complexity on the client. If you stream tiny pieces, you get immediate feedback but more UI updates. If you stream big pieces, you lower update count but delay the first reveal. The intuition is simple. Let the model or simulator send text as pieces. The client assembles those pieces into a visible string as they arrive. This shines when users need quick feedback, like chat interfaces or progressive summaries. A key limitation is ordering and state. You must maintain sequence and reconstruct reliably. And you may need to balance size versus update cost. We will keep the same example message through every step so you can compare results. We will stream a long message in small chunks and assemble it on the client for snappy first paint. First, we split the message into parts for streaming. This snippet chunks text into fixed pieces and reconstructs the output. It prepares the string text, then uses a list comprehension to slice fixed size pieces with a range step. The variable parts holds these sequential chunks, which is the typical shape of streamed tokens. Joining parts with an empty separator builds out, restoring the original message exactly, mirroring how a client assembles partial responses from a model without waiting for the full payload. Increasing the chunk size reduces UI update frequency because each piece contains more characters, while decreasing it increases granularity. The printed line confirms the restored output and shows the assembly worked. Next, we model how latency affects perceived responsiveness. This snippet estimates time to first byte and total streaming time using a simple arrival model. It assumes each chunk arrives after a fixed delay and computes the number of updates based on the text length divided by a 6-character chunk, using a ceiling to count partial chunks. The variable delay represents per chunk latency, so time to first byte equals 1 delay, and total equals updates times delay. This simple model helps reason about perceived responsiveness versus completion time before wiring real network I/O. Increasing delay increases both numbers linearly. Increasing chunk size lowers updates and shortens total, while time to first byte stays the same. The printed metrics quantify expected response times for planning. Now we compare options to choose a good chunk size. This snippet compares chunk sizes and selects the fewest UI updates for a given text. It defines a list of candidate sizes and builds pairs of size and update count, where updates is the ceiling of characters divided by the candidate size. The resulting list captures the trade-off between granularity and the number of render passes. The selection step picks the candidate with the smallest updates using a simple minimum with a key. You can add more sizes to the list to broaden the search. Choosing a larger chunk reduces the number of updates and the frequency of heavy DOM work, while a smaller chunk improves early context. Next, we reduce visible churn with client-side batching. This snippet shows how batching multiple small chunks before rendering reduces visible updates. It keeps a small chunk size for fine control, then groups several chunks into one render pass on the client. The variables updates B1 and updates B2 compute how many UI updates occur with a batch size of 1 versus a batch size of 2, illustrating the math behind fewer draw calls. Batching typically halves the number of renders here and so reduces flicker and layout churn. Increasing the batch size lowers updates further, but delays each refresh and the perceived responsiveness. Decreasing the batch size refreshes more frequently at the cost of more work. The printed numbers highlight the trade-off clearly. Finally, we show a first paint trick to feel instant. This snippet renders only the first few chunks for a snappy first screen. It uses the function iSlice, which takes a slice of an iterator to cap the number of chunk steps and assembles those pieces into out for the initial display. The variable n controls how many updates are emitted before pausing or awaiting more data, modeling incremental UI drawing and first paint behavior. This forms a minimal baseline. Stream tokens, render a bit, then continue as more text arrives. Increasing n shows more content initially, but takes longer to display the first screen. Decreasing n speeds first paint at the cost of partial context. The printed line reports the updates used and the visible text. Recap in 3 points. What it is, streaming breaks responses into pieces so clients assemble them progressively. When to use it: for chat, summaries, or any interface that benefits from fast perceived feedback. One caveat: small pieces increase UI work and require careful batching and ordering. Next step: tune the batch size and measure time to first byte and total completion across realistic delays and chunk sizes to find the sweet spot for your UI and network conditions. If practical AI engineering like this helps you, subscribe and watch the AI engineering videos.